Believe it or not, it's a tiny microscopic heart beating inside every single piece of modern technology you own.
All right, today we're diving deep into the absolute core of modern electronics, the PN Junction. So what is it? Well, it's basically the tiny, invisible gatekeeper that makes everything from your phone to a supercomputer possible. How? By controlling the flow of electricity inside every single chip.
So, how does this tiny marvel actually work? Well, first we're going to look at its two essential ingredients. Then we'll see what happens when they meet and form this natural barrier. After that, we'll learn how we can open and close this gate, discover its amazing relationship with light, and even see what happens when metal meets silicon. Let's get into it. Okay, first up, the heart of electronics. Before we can build our junction, we need to get to know the two specially prepared materials that form it, P-type and N-type silicone.
So here's the deal with pure silicon. On its own, it doesn't conduct electricity very well. To make it useful, we have to dope it, which is just a fancy way of saying we add specific impurities. If we add acceptor atoms, we get P-type silicon, which has an excess of positive charge carriers called holes. A great way to think of this is like a parking lot with a bunch of extra empty spaces. On the other hand, if we add donor atoms, we get N-type silicon, which has an excess of negative electrons. So that's like a parking lot with extra cars circling around, just looking for a spot. So you've got empty spaces right next to extra cars. What do you think happens next?
Okay, let's talk about that built-in barrier. This is where the real magic happens, right at that interface, the very instant these two materials touch.
The moment they touch, physics just takes over. Those extra electrons on the N side, they see all those empty hole spaces on the P side, and they just rush across the boundary to fill them. It's a process called diffusion. As they cross, they basically cancel each other out, and this creates a depleted zone right at the junction, where there are no free-moving charges. And this creates a spontaneous static barrier, a built-in electric field, that immediately stops any more charges from crossing.
And that zone right there, that's what we call the depletion layer. It's a region that's been stripped of any free carriers, so it acts like a natural, self-forming insulator. It's like an electrical gate that slams shut all by itself.
Now, this barrier has a very specific strength, a voltage we call the built-in potential. For a typical silicon PN junction, it's around 0.9 volts. The best way to picture this is to think of it like a small dam. The electrons are the water on one side, and to get to the other side, they need to gain enough energy to get over this 0.9 volt high dam. So we have this dam that builds itself. That's cool and all, but the real power comes from being able to control it, right? To use an external voltage to open the gate and let current through, or to close it off even tighter.
And you know what? Controlling it is incredibly simple. If you apply a positive voltage to the P side, you're essentially giving the charges a push, which lowers our dam. This is called forward bias, and it opens the gate, letting current flow easily. But if you do the opposite, apply a positive voltage to the N side, you pull the charges away from the junction, which makes the dam even higher. That's reverse bias, and it's like closing and locking the gate, blocking almost all current.
You know this whole one-way street behavior? It actually has a name, rectification. It just means that current can flow easily in one direction, but it's blocked in the other. This is the absolute core function of a diode. It's an electrical one-way valve.
So why does this matter to you? I mean, really? Well, just look at your phone charger. The power coming out of your wall is AC, alternating current, meaning it flows back and forth. But your phone's battery needs DC, direct current, flowing in only one direction. The PN junction diode inside your charger is that one-way gate. It lets the current flow in, but not back out, converting that AC to DC. That's rectification in action, every single day.
Okay, this is where things get really cool. Let's talk about light. Because this simple junction doesn't just control electricity, it can also turn light into electricity and electricity back into light.
Think of a solar cell as just a really big PN junction, designed to just sit there and soak up sunlight. When a photon from the sun smacks into it, it has enough energy to knock an electron loose, creating an electron-hole pair. The junction's built-in electric field, our dam, immediately grabs them and separates them, sweeping the electron to one side and the hole to the other. And that separation of charges, that is an electrical current. Boom. Just like that, you've turned light into electricity.
Now, what if we run that whole process in reverse? Well, that's exactly what an LED, a light-emitting diode, does. We apply a forward bias, pushing a current through the junction. This forces a whole bunch of electrons and holes to crash into each other and recombine. When they do that, they have to release their extra energy, and they do it by spitting out a photon, a particle of light. Electricity becomes light.
I mean, look at this. It's just so elegant, right? The symmetry is perfect. A solar cell takes in light and spits out electricity. An LED takes in electricity and spits out light. It's the exact same fundamental process, just running in opposite directions.
So that begs the question, right? How do we get different colors like red, green, and blue? Well, it all comes down to something called the materials band gap. You can think of it as the specific amount of energy the electron has to release when it recombines. By choosing materials with different band gaps, like gallium arsenide for infrared or gallium nitride for blue, we can precisely engineer the energy of that photon and therefore the exact color of the light.
All right, one last thing, just to show you how deep this whole junction idea really goes.
Get this. It turns out you don't even need both p-type and n-type silicon. If you just join a piece of metal directly to a semiconductor, you get a very similar effect. A one-way barrier, called a Schottky barrier, forms right at that interface. It's the same core idea, just with slightly different ingredients.
And look, these aren't just some obscure scientific curiosity. They are absolutely vital. They help us create perfect electrical connections where we need them, and their properties are critical for squeezing every last bit of performance out of the high-speed transistors at the heart of every single computer processor.
So when you step back and think about it, it's pretty mind-blowing. The simple act of joining two materials together gave us a one-way gate, a solar cell, and an LED. It literally turned a slab of silicon into the engine of our entire information age. Which really makes you wonder, what new kind of junction, what new fundamental building block is going to define our future?